Great, thank you all for coming to this talk at the end of a very full and exciting day. And I'd like to thank the organizers very much for the invitation. And I'd also like to thank the organizers of the entire SRI for a truly wonderful event that'll leave us all with a lifetime of memories. And I came as a graduate student to the 1995 edition. I've been to everyone since. And 1995 was for me a mind-blowing experience and formative in innumerable ways. And I'm happy to tell you about it afterwards, but this one really is fantastic, and I'm very happy to be here. So before I forget, I just want to mention that I'll be mentioning work of many people often in passing, but this is also joint work with Hannah Larson and separately with Jim Bryan. And I also want to mention some work of Ben Church. So I'd like to tell you some fun constructions and facts to help me understand a bunch of ideas much more clearly. So what I'd like to do is give you some understandable proofs that you can remember and take home, where I'll tell you the important parts, and the omitted parts are genuinely, as far as possible, straightforward. But so in particular, this talk is not intended for experts who are going to be bored, but for people farther from the area or newer to these ideas. And some of my personal mathematical philosophy is behind this, which is that I think that important mathematics, even if it's well known to the experts, should be constantly broken down and digested to be made more and more elementary and transparent, because better understanding develops our intuition and ability to advance frontiers of our knowledge. Okay, so let me begin. So there's a repeated theme in algebraic geometry, which is that topologists can make arguments in a style that we cannot. So forget the proofs, even the statements we have trouble with. Stabilization results are one in particular. And one, for example, that's very motivating that I'll shed no light on whatsoever today is horror stability, which is that as the genus goes to infinity, the moduli space of curves stabilizes to something particularly nice. And it's sort of very interesting and challenging that we have a hard time saying things that have been interesting in recent years when algebrogeometrically we've been able to, not me personally, but in fact some people in the room, to actually make algebrogeometric sense of what such stabilization actually means. So more generally, there's this notion of stabilization that comes up repeatedly in mathematics, which is in algebraic geometry in particular, where you have some family of problems where the answer is nice, but only becomes perfect somehow in the limit where it reveals its true magical structure. So so stabilization results in algebraic geometry come in many flavors. So some of these were discussed in a number of talks earlier on, and for example, in Jordan Ellenberg's talk earlier in this session, there are a lot of themes that I'm going to end up hitting on again later on, where you have a sequence of moduli problems, sequence of questions, and you have stabilization or close approximations or limiting behavior. And the question, and it's interesting to see when you get such stabilization, when the stabilization in what regime it works, where we're able to prove it, where we believe it or unable to prove it. And so often they're cohomological in nature, where we have isomorphisms of cohomology, perhaps in a range. And then there's often these are only rational cohomology with rational coefficients, or rationally if we're in QL, or sometimes it can be integrally. There's this question of rings or groups, Hodge structures, Chow rings. There are questions about point counts that sometimes stabilize. I've been interested for these reasons in classes of Godin ring. But homological things are not as good as homotopical things. And so analogous homotopical things are when things become over the complex numbers more and more highly connected or homotopic. And then there are more algebraic analogs of these things that we're used to working with as well. Some are elementary, some quite fancy. And I'd put things like the derived category also in this homotopical setting as well. So it's always interesting to state results as far sort of upstream as possible. If someone tells you something, if you get stabilization in cohomology with rational coefficients, you always want to ask, is it true critical coefficients? And you also want to ask, is there some underlying homotopical statement as well? So my goal is to give you a setting that's something short of isomorphism that's going to be upstream as possible. So to get there, I want to make I'd like to first make some naive definitions, a very naive version of K-connectedness in the algebraic setting. Then I'll define three categories of spaces. First, roughly So first, roughly in varieties, a very mild special case of in varieties, then to say what I mean for stacks, and then to get to the third and final category, which I want to really do business, which is this, which is a homotopia category. And the point about and I'll give examples to ground and motivate the definitions, and these are going to be really simple-minded things, and that's intended to be, and that's intentional. So I'd like to be able to discuss things in a more flexible setting than varieties or stacks, where we can still use various words such as chow rings, Hodge theory, point counts, Picard groups, and so forth. I'll define a naive, looser setting in which we can work over various bases and then use the same language we would use for varieties. But the point of this is something which is simple-minded, and the point of being simple-minded is that it's robust and thereby versatile. So for simplicity, I'm just going to talk about smooth things. I can discuss later how to deal with things with singularities, and I'll have some technical hypotheses that stacks we'll talk about that will be finite type that. Basically, don't worry about this unless you actually want to. Okay, so let me get down to business. I like to make the setting by describing these kinds of just easy to define class of morphisms and these fairly easy to find categories of spaces. So I want analogs of connected maps in topology that are very naive analogs. So connected map in topology will be something that will have isomorphisms on the first homotopy groups. So let me tell you the properties I want them to satisfy, and then that becomes a definition. So I want to say something. A morphism is K connected. Well, I'll just give you some examples. Affine bundles, AN bundles in the topology. Affine bundles should be homotopically the same thing, and they should be, and so these should be K connected for all K. I should say before I go on, I want to previously say that I want all sorts of notions to be well behaved with respect to anything I say. So maybe you personally might want to pick your favorite thing in this list of desiderata that you want spaces to have. Maybe they be child groups or over the complex numbers, some third cohomology group or anything, and make sure that your personal choice is cheaply well behaved in the setting I'm talking about. So affine bundles certainly preserve these properties that we want. Secondly, if X is an open subset of Y, and I've thrown out a co-subset of codimension bigger than K, I want to declare that to be K. And then finally, if I have two morphisms whose composition is a third, of those three morphisms, two of the three are K connected. The third shouldn't. You can take a variant of this rule, but this will do the job. And then I'll just make this the definition. K connected morphisms is going to be the smallest class morphisms containing these that satisfying these three rules. And then you can check for some examples that projective space Pn sitting in any larger projective space sitting linearly in that way, that's an n-connected morphism. Or BGLN inside a larger BGLN, it's a BGLN plus one, that's n-connected as well. And then you can check that this notion behaves the way you might want it to. So for the complex numbers, these such morphisms are also topologically K connected. And then one special case I'll just need for technical reasons later on. An example of a special class of these K-connected morphisms that are particularly nicely K-connected are the following things. They're morphisms where you have an affine bundle. I have my tablet here for a reason, so let me actually use it. So you have an affine bundle, and I want an open subset of the affine bundle where fiber-wise, I'm throwing out a complement of codimension bigger than K. So I'm throwing out only a high codimension subset. And so I want these morphisms and composition of these morphisms are going to be a particularly nice class, subclass, which is preserved by base change. Okay, so that's my set. And now we know what naively K-connected morphisms are. Right? The first category I want to when a set are somehow there's in varieties or in spaces, but just which I think of as Cauchy sequence of spaces. But there are slightly special in spaces where I just have whoops, I do not want to erase. I want to. I have an algebraic space closed embedded in another one, in another one, in another one, a sequence of closed embeddings, and my one extra thing beyond the definition of an in variety or in space is I want these inclusions to be more and more highly connected. So this is my object in my category. This is if you're comfortable with in varieties or in spaces, it's a special case of one. And as examples, P naught sits inside P1, sits inside P2, and so forth. These guys get more and more connected. This is an object which deserves the name P infinity, or you could take the Grassmannian Gn and Gn plus 1 and Gn plus 2. These get more and more highly connected. This deserves the name Gn infinity, or you could take G12 and G24 and G36 and so forth. That also is a reasonable thing. And I just want to point out that because K-connected morphisms are nice, we immediately have, each of these things have, over the complex numbers, they have underlying topological spaces, for example. And now things like, they also have Chow rings, they have cohomology rings, everything just, these objects just naturally have all the properties that you want. And so to make sure we understand it's a category, if you take one of these Cauchy sequences, one of these objects, another, what are the morphisms? I don't necessarily need them to map nicely. They just have to map, they just have to map any old way in some increasing way with some equivalence relation, such as, for example, the morphism described as is on the screen. I could shift this morphism up to this morphism, and that would be declared as the same. So if you think about it, the notion of this category is not so hard to think about. It's basically a full category of invarieties. Okay, so that's my first variety like space-like category. So now let's take this. Now let's take this to stacks. And now I want algebraic stacks, and I want to do something similar. So my Cauchy sequence of stacks. And now I just want them to be separated, but again, I want them to be, these morphisms to be highly connected. And now there, for reasons of things, for a number of reasons, it will be convenient and important that this is, you need more than just simply the sequence of increasingly connected things. I'm going to need to have the existence. I want to have a Cauchy sequence of stacks that comes with something which maybe I'll call a spatial realization, which is a map from, in this case, I want my things to be vertical from one of my Cauchy sequence of algebraic spaces. So in other words, there's my sequence of spaces, and now the one special thing is I want these vertical maps to be open subsets of one of these special kinds of maps. So they're essentially affine bundles minus high dimension codimension minus high codimension subsets. So the way you should think about these, and everything in sight is getting more and more highly connected as you get further on. So these maps here become closer and closer to affine bundles, basically, as you go further on, and these all become highly connected. And I'm going to skip some things that are, it's not hard to verify, which is that if you have a Cauchy sequence of stacks for which there exists such a spatial realization, a realization by spaces, then any two spatial realizations are dominated by a third. And so in effect, these guys are almost unique. The spatial realizations connect you to the world of topological spaces. They give you something concrete to hang on to. I won't say too much more about that, except that you actually need them. And just to say that the morphisms of Cauchy sequences of stacks that have spatial realizations, the morphisms, the rules are just the same. But the main thing is the examples will tell you how they should work. So for example, the stack BGM, well, I'll think of it as a Cauchy sequence of stacks, except that every single one is BGM. But now my spatial realization will be P infinity, P naught, go to P1, go to P2. And all these maps are getting more and more high. Well, these are extremely connected because they're isomorphisms, but all these other maps are getting more and more highly connected. Or BGLN has its spatial realization GN infinity. Or I now have a new creature. Whoops, this guy keeps racing. Now here's a new creature, a new object I can now talk about formally, BGL. What is BGL? Well, it's a sequence of stacks, BGL1 to BGL2 to BGL3 and so forth. It's anchored to some spaces. G12 goes to G24, goes to G36. And so that now I can talk about BGL fully in our algebraic world. I don't have to I don't have to just let the topologists own this notion.
But I could choose not to call that BGL infinity.
I could call it I would call BGL infinity as well.
Okay.
BGL equals BGL infinity. In the same way that, yes, that's a reasonable thing. Later on, O will be O infinity and things like that. I'm using that convention. And then any of our objects in this category, they have Chow rings, they have Hodge, they have H if over the complex number, they have atypical homology, they have Frobenius actions, they have point counts, if you say that the right way. And how do stacks have point counts? Well, the cheap thing is that the varieties have point counts. That the algebraic, these have point counts, and these have relative dimensions. So you can actually make sense of point counts, Frobenius, everything you want. Derived categories of coherent sheaves make sense on these things. Any Picard, anything you want, just you can make sense. You have to think a little bit about how to behave with respect to these limits. But the point is, it's not nothing fancy has happened. And now my final category that I want to live in is this homotopy-like category. It's not really a homotopy category, so don't sue me if you're a topologist. But I just want to take my category, my Cauchy sequence of stacks, and if I have a morphism of one to another, I should say, I know when a morphism of these guys, let me go to a morphism. I know what it means for a morphism to be, of this Cauchy sequence of stacks to this Cauchy sequence of stacks to be 5 connected. It means that when these maps, as I go further and further on, eventually they're all 5 connected. And more generally, I know when a morphism of a Cauchy sequence of stacks to another Cauchy sequence of stacks is K connected. And so in particular, I wanted to say if something is, I want to take all the morphisms that are infinitely connected and declare them isomorphisms. I want to formally invert those morphisms that are infinitely connected. And that is my homotopy category. And so now what I've done is I've turned P infinity is now isomorphic to BGM. That's a rigorous, well, it's by definition almost tautological. It's not a tautological statement. But now I can say rigorously P infinity is BGM, Gn infinity is BGLNN, G infinity, infinity plus infinity is BGL infinity. These are all isomorphisms. And again, all the objects in this category have all the geometric notions we wanted, homology groups, you name it. In particular, they have homotopy types, they have Chow rings, everything's integral. And everything I'm saying is super cheap. And there's one exception. There is a functor to motivic spaces from here, and this is now out of my wheelhouse. So Ben Church has proved that there's a functor to motivic spaces, and because connectivity, A1 connectivity is more complicated than usual connectivity, a trick is needed where he needed to do the map to motivic. Well, it's a homotopy category of motivic spaces. To be honest, from the homotopy category to there's a functor from G from the homotopy category to the homotopy category of motivic spaces, where he needs to double suspend, and then there's and then you get a map to motivic spaces. Am I lying, Ben? No, good. I'm not lying. Good. Okay, so that's the one significant fact, but everything else I claim is you can just do yourself. And I want to just point out that this contains implicitly many classical constructions. So just as 2 examples, things like so in Andrew Kresh's PhD thesis, he introduced Chow groups for Artin stacks with integral coefficients, and in it for reasonable Artin stacks, which are reasonable for a wide class, which are really the ones that all normal people do business with, his definition, his construction is this construction. You take the Artin stack and it literally is this construction. Or the way we have equivariant Chow groups for varieties, Edidin Graham's construction building on Totaro is this construction. If you just put it in this feature and you just take homology, it just is without change. And I don't mean to say that what I just presented is super fancy and clever because it includes what they did. It's more that what they did is super fancy and clever, and this simply puts what they did into a convenient convenient package. Okay, so all that was intended to set us up for something in which we can now actually make statements. And I wanted to be honest about it, so rather than simply invoking things. But I think I've been honest. So let me give as a first example bot periodicity. Let me state first of all that with bot periodicity, it's something that you may not if you're like me or other people, it's something you may not have seen except briefly in graduate school, and maybe in graduate school you didn't think much about it because it looked as though it was far from algebraic geometry. So I'd like to give a very brief explanation for it in case you haven't seen it before, because it's something that I had that I certainly needed a refresher on. So Bott periodicity is one of these fundamental results in topology and K-theory. And the way, at least I had seen it, it was presented as a very analytic or topological result that was not really part of algebraic geometry. But it's such a fundamental statement that it looks like it comes from algebraic geometry. And the case I'm going to make is that it actually is most simply an algebrogeometric statement. So what is it and where does it come from? Well, the way I would say it is a historical and fake, which is, so consider 100 by 100 orthogonal real matrices. And look at this group, and if you're to sit down and calculate the first homotopic groups by hand, and take some time, you do write down the first 24, and you compute these groups, and you notice that there's this pattern. It appears to repeat mod 8. And then you'd realize, you keep on going and you realize the pattern doesn't go on forever. And you would immediately know what to think, which is that the reason it doesn't go on forever is because 100 is not big enough. And that somehow as 100 gets bigger and bigger and bigger, the pattern should go on longer and longer and longer. So implicitly, you're thinking that there should be some sort of topological stabilization going on. And indeed, when you take pi, there should be the limiting space O of infinity, or just O, then its homotopy groups do repeat mod 8. And so that's a beautiful fact, but it's a shadow of the more beautiful fact that in fact, what happens is there are 8 spaces in a row, except they're not spaces, they're homotopy types. And so there's O, which is O of infinity, and they have the property, these homotopy types, that when you take loops 1, when you map, we're out of algebraic geometry land for a little bit. When you take loops into each one, you get the next one. And so when you do this 8 times in a row, you return to where you started. And because homotopy groups behave well with respect to taking loops, they just get shifted by 1. This explains the 8-fold periodicity of homotopy groups. But really the fundamental fact is that there should be 8 homotopy types in a row, which you loop around in this way. Each one is loops 1 of the previous one. And there's a simpler two periodicity with the unitary group as well, often called complex periodicity. So that's Bott periodicity. And I'd like to present two periodicity and say what algebraic geometry really is. So what it is, I'm going to say it in its guise that rather than loops 1, I'm going to talk about loops 2. In some sense, I won't say too much about it, but loops 2 is what really matters. One of these loops 1 is really obvious and tautological, and it's the other loops 1. It's some of the loops 2 captures everything. So I'm going to try to explain that why loops 2 of BU is BU roughly. I'll omit the Z for now. Or since the unitary group is something I don't understand, depends on algebraic geometry, I'll replace it by its homotopy equivalent over GL. So I'll explain why loops 2 of BGL is BGL. Okay. So now comes to something, if you were tuning out a little bit because there are non-algebraic things, we tune back in, because what I want to say about this two-step periodicity is that it's at heart something about that's sort of extremely hyperclassical algebraic geometry, which is it's about essentially an isomorphism, not essentially, it is about a near isomorphism of moduli spaces. So it's that there are 2 different moduli spaces that they're not in terms of N and D. And I'll tell you it's on the screen, but they're not isomorphic, but they're very close to isomorphic to each other. And that this near isomorphism plays well with increasing N and D. And so as the N and D get bigger and bigger and bigger, they converge. It's a Cauchy sequence. They converge topologically. They get closer and closer to each other. So to say it again, the first space is the moduli space of just vector bundles on P1. What can be simpler or more what can warm our cold hearts more than this? Then moduli of just vector bundles on P1. Degree D rank n vector bundles on P1. Trivialize infinity is the base point. Take that moduli space. So one of the lovely and the other moduli space is just BGLD, moduli space of degree D vector spaces. And the point is these 2 moduli spaces are very close to each other topologically. And in other words, they're almost isomorphic. And the minute I say this is a great puzzle to go home and think about, which is why are they the same thing? So what's really going on is there are these 2 moduli spaces, And there are two affine bundles over the roughly affine bundles up to extremely high codimension. And these affine bundles are almost the same to extremely high codimension. So you have two moduli spaces that are almost the same. And this is what I'm going to explain to you why they're almost the same. I claim that is Bott periodicity. And this almost isomorphism is so natural that it behaves all with increasing N and D. And when you take the limit, then this almost isomorphism becomes an isomorphism because they agree up to higher and higher codimension in some sense. And then that the resulting thing in our category is that algebraic loops to BGL is BGL. And so all we do then is we just look homotopy. We specialize. This is over spec Z. This has nothing to do with complex numbers, any field. This is just a very general statement over an arbitrary base. But we now specialize to the complex numbers, take homotopy type, and now the thing on the left is homotopy to the thing on the right. And there's a very small extra thing, small jump to make, which I'll mention at the end, to get from algebraic loops to actual loops too, but that's cheap. And I'll just stick to the fun stuff for now, which is what's the link between these two things? So given a degree D rank n vector bundle on P1, how do you get a rank D vector space? Well, I'll tell it to you to first approximation. I'll map. So basically, it's saying let me map a test variety to this and to this, and it's basically I'm asking for a recipe, roughly speaking, since this is going to be some hand waving going on. If I have a family of vector bundles, degree D rank n vector bundles on P1 over B, I want to get a vector bundle. And what is that vector bundle? It's essentially, it turns out it's just push forward. In fact, push forward works, although it's the wrong rank. But push forward E-1 is what actually works. And the one caveat is that in order to actually get a vector bundle, you need to have started with a relatively globally generated vector bundle. And so all that means is I need to take a very big open set here. And again, all I'm trying to do is to show that these two things are the same up to high codimension. So that's actually not cheating. But let me give you a better explanation as why two things are the same. I'll tell you what this magical thing on top that is essentially an affine bundle over these two things. It's a quiver representation. The representation of this quiver, where it's got, so it's the moduli space of two vector spaces. One vector space is A of dimension D. Another vector space is U with bases. So it's a fixed vector space. And I want furthermore a linear map from A to itself and a linear map from A to U. And I claim that this quiver representation that's the thing that is here, and I'll tell you how to map to both things. So to map to get a rank D vector space out of this data, you just remember the vector space. And from this, how do you get a vector bundle on P1? Well, you build a vector bundle on P1 from this data as follows. You take the trivial bundle take the trivial bundle on P1 with fiber A. You take the trivial bundle, you twist it by -1. You take the trivial bundle on P1 with fiber A and U. You just map using x0 and x1 are coordinates on P1. You map by this map, and you have to check this. I'm just telling you this, but you have to. The cool thing, this is a theorem of, I think Stroma was the first person to see this construction around 1980. It turns out you take this construction, take the co-kernel, the co-kernel is a vector bundle of degree D and rank n. And this is kind of this is a neatly reversible thing. So the point about this is that the reason these two are almost the same is because there's something magical that is essentially an affine bundle over both that comes from a quiver representation. And the clue to it is that these two are supposed to be almost the same, and you just need to figure out what that is. So this is the first of roughly 4 examples of the sort I'm going to show you. So, but just to say it again, Bott periodicity, at least this twofold one, for example, has nothing to do with the complex numbers. It's just about vector bundles on P1 and vector spaces. It's about this one very simple quiver. There's a small step at the end to get from algebraic loops to regular loops to, which you might think is scary, but this is something that's actually one of the oldest things that can be done in topology. You can really do it by hand. There's an argument by Stephen Mitchell, which I really like, in algebra geometric language, but Cohen, Lukircho, Siegel also have a very short argument, something you just do by hand. and somewhat more using using exactly the same construction, basically, but more sophisticated thinking. This is how Ben Church shows that this is the same bot periodicity you get for motivic spectra, except in this case, we have it even for the homotopic category of motivic spaces. Okay, so that's great. So that's that form of bot periodicity. So now let me tell you another classical result that I want to give you essentially a proof of and tell you how to think about it this way, which is going to be vector bundles on a curve. Maybe for experts, you think about, I'm going to do GLN. You can think about orthogonal and symplectic, where things get interesting. And I can even spell this correctly, maybe. There we go. Okay. So, so for now, I want to fix a smooth projective curve of genus G, say genus fabric is not relevant, and P is a point on the curve. And then I'm going to call Bunard space of bundles, rank R and greedy bundles. And in the bundles, I mean all bundles, period. That's a partly stacked, non-quasi compact partly stacked, beautiful space. In it, you have got the stable bundles. I'm not going to define, it's not going to, it doesn't matter what the precise definition if you haven't seen it before, but it's an open subset. And it's a neat, an important fact about it, that if R and D are relatively prime, the stable bundles form a projective variety. And there's this, in this totemic paper of a TN bot, they showed, among many other things, that, well, in this case, this was over the complex numbers, that these projective varieties, as you increase the rank, the dimensions get bigger and bigger and bigger, but that these moduli spaces topologically stabilize. This is a topological stabilization. And I want to essentially give you the proof. And try to convince you that this is somehow algebraically an extremely natural fact. I should say a TN bot do more. We can do more too. Like you can see the cohomology of this space, the car group of this space, including for other groups. But time is short. I just want to tell you how this works. And so, because when you do it, there's some insight I didn't have until actually realizing how it worked. So the relevant thing is the first thing you do is nothing I do is going to be shocking. Instead of bundles, I'm going to take frame bundles. Bundles where at P, we're going to ask that I'm going to identify the fiber over the point P with, I'll say C to the R. This isn't about the complex numbers. I'm just using the complex numbers to avoid being precise. All this works over arbitrary basis. So I'm going to trivialize, have a choice of, I'm going to identify the fiber over P with rank R 3 vector space. And so I also going to want coherent sheaves of rank R and degree D on the curve, which is and framed at P. And just to be clear, I've got my curve. So the fact that it's coherent, not just a bundle, means that I'm allowing torsion. But the fact that it's framed at P means that it means that I'm allowed to have torsion at various places, but I can't have torsion at P because it's supposed to be framed to be rank exactly R at P. Okay, so these are wonderful. These are lovely spaces. They're as stacks. They're smooth dimension 0 stacks whose dense open subset is a point. It's like a partial compactification, or I've heard the word enlargement of a point. So it's a point which is boring topology. You've glued on some negative dimensional stuff, give it some interesting topology. So these are two beautiful spaces. And so, and then it's cheap, and they're smooth. I did say they're smooth. And so it's cheap to check that when you let the rank get cranked up, the stable bundles get closer and closer. The complement of the codimension of the complement of the stable bundles in all bundles goes to infinity. And so if I want to show that these guys stabilize, I can show that these guys stabilize. But then these guys are a GLR bundle over it. So it suffices to show that the frame bundles stabilize. But then the codimension of these guys inside the coherent sheaves goes to the codimension of the complement. This is open inside here, and the codimension of the complement goes to infinity as R gets big. So it suffices to show that these guys stabilize. And that's what I want to show. And then the fun thing is that I want to show they stabilize, but they don't just stabilize, they're all isomorphic. Not as stacks. They're not, I'm sure, I don't know why. I'm sure they're not isomorphic stacks. They're all zero-dimensional smooth stacks, but I'm sure they're not isomorphic. But they're isomorphic in our naive homotopic category.
so long as the rank is bigger than 1. And so these are all isomorphic. That's what we want to prove, so long as the rank is bigger than 0. And furthermore, they're equal to the colimit when the rank is 0, essentially of the space of coherent sheaves like that. Okay, so let me prove this for you, or sketch the proof. I think this is going to work. I think so. So how am I going to prove this? So here's the result I want to prove. So I want to show these are all isomorphic to each other. Instead, I'll just take one of them and show it's equal to this colimit. And I guess there's all sorts of things I'm omitting because it has to be the colimit in the same way. And so I'm just going to fix one of these guys and describe it as a colimit, and then leave out the fact that that's enough to do. So I'm going to fix R and D, show that it's going to be some limit of these things. And so how will I show it some limit in this homotopy category? Well, I'm just going to show it. I'm going to show that they're isomorphic at the high codimension or at finite level. So how will I do that? I will just, so the space of coherent sheaves of rank R and degree D, those coherent sheaves, I can twist them by O of P a lot and crank the degree up and have the same moduli space. So from that point of view, I can change the degree as much as I want. So I might as well assume the degree is really, really huge. So then among all the coherent sheaves of this sort, the globally generated locus is almost all, it agrees with it up to a locus of extremely high codimension, which I don't care about. So I'm just going to talk about globally generated coherent sheaves of rank R and degree D, where D is huge. Okay, so in this globally generated locus, I want to take an affine bundle over this, which in my homotopy category, doesn't change it. What's my affine bundle? I want the additional data more than this sheaf. I want the data of a splitting. I've got this nice exact sequence of my coherent sheaf E, my restriction to P, and well, yeah, this, this exact sequence, and I would like to take the choice of a splitting. And the choice of the splitting, well, that's an affine bundle because this is a vector space of constant dimension. This is a vector space of constant dimension. This is a splitting of relative dimension, this dimension times this dimension. So I will instead consider the moduli space of globally generated coherent sheaves of this sort along with the splitting. But this data of this, well, this splitting, that gives me R sections of E, R sections of E. And these R sections of E are an isomorphism at P. And so this map is injective because OC is torsion free. So this is injective. So if this is injective, this map is injective. It has a co-kernel. This co-kernel is this is rank R degree D. That's rank R degree 0. That's rank 0 degree D. It's got a co-kernel, which is a coherent sheaf, which is completely torsion. It's rank 0 degree D. In other words, the data I'm thinking about is exactly the same as data like this, which is the data of a torsion sheaf, not supported at D, along with an extension class, X1 of this by this. Again, affine bundle. This is a constant dimension vector space. So in other words, an affine bundle over this space is equal to an affine bundle over this space. So they are isomorphic up to some high codimension. So that's basically it. I've showed that this space that co-RD and co-0D are up to high codimension the same. This is the same if I put it this way. This sounds very similar to my plot periodicity argument. I now have to be careful that what I'm saying plays well with increasing D and increasing everything else. So there is something to check, but it just works. That explains why the theorem is true. And I should say that we get a whole lot more, like you can see the cohomology of the space, you can see the car groups of these space. Maybe the one feature I'll say is that this relates actually to something that Jordan said in his talk as well, which is, I said fix a curve C in a point P. Well, the construction it just works over an arbitrary base and even as C and P vary. So this works not just over spec Z, this works over, what did I need? This works over MG1. Universally over spec C. Well, I need to be really careful. Somewhere I use the fact that the tangent bundle of the point was trivial. So technically it's a moduli space of genus G curves with a marked point and a marked tangent vector. So this is over MG1 with a tangent vector. So it's like the mapping class group. Question? Good you see as a curve. Yes, if it did you see as a curve, you need to see the curve
Oh, sorry, the question, I believe the question was, did I use that C as a curve? In this, yes. Did it absolutely use that C as a curve and used, doing it, that even that as a, I should be a bit careful. Good question, did I use that as a smooth curve?
Yeah.
It had to be smooth at P, to what I was doing. Oh, yes, because the torsion sheaves, let me think about that. Right, then I think that is an awfully good question. I should have been correct. So I feel like something interesting wrong will happen if it's not smooth. The point of singular, but I have to actually fix something. Yeah, great. So where does this, what goes on? That's a fantastic question. Great. So great. So maybe it's even over something bigger than this. I need to be a bit more careful. But it just at least automatically works. It's not characteristic zero. It's not complex. And to get the Tiabat result, you specialize to the complex number, specialize to homotopy type, and then it's home free. And a puzzle as I was preparing this talk on the weekend was that I realized that this suggests the existence of other spaces which should also be homotopy equivalent, whose existence I never really thought about. I'm not sure if I have the right definition, which is the Bott periodicity result and this result here are about maps of pointed curves to some space, and the space parameterizes not vector bundles, but coherent sheaves. But you need to be a bit careful what these coherent sheaves are. For the sake of time, I'll say it briefly. You can ask me afterwards. But these are kind of enlargements. I want to almost say partial compactifications of BGLR. And so the BGLNs get all definitely converge to BGL infinity or BGL, but I think they should all be open into these very nice stacks. And then these very nice stacks, all of which are not isomorphic to each other, but all of which should be isomorphic inside our homotopy category, and hence which they're going to be isomorphic in all nice ways. And in particular, the coherent sheaves. Now here I do need the curve to be smooth for this statement. The coherent sheaves of rank R and degree D are a part of morphisms to this magical stack. And all my previous statements, Bott periodicity this, come from the nice property of this stack and maps of curves to these stacks. Okay, but that was an aside. Let me go to the full Bott periodicity, which is the eightfold coincidence with, and I'd like to give you one example of it, and I also want to. There's one part, the very final part of the argument. There's like one thing that I'm stuck on and I feel like if I were to ask this audience, someone in the room is going to recognize it and will help us out, and we'll finish the proof. So let me just so let me first tell you what loops. So let me explain to you from this point of view why loops 2 of whatever this is, SP mod U, is BO. And I'd like to. The point is I want to tell you what nice finite dimensional moduli spaces and beautiful classical geometry it is, and what surprising fact it encapsulates. So this is the thing I want to describe, and it's going to be algebraic loops and so first let me just tell you / remind you what the Lagrangian Grassmannian is. So if you fix a dimension 2n vector space with a non-degenerate alternating pairing, then the Lagrangian Grassmannian parameterizes half-dimensional, n-dimensional isotropic subspaces, maximal subspaces, and so that's really, which is an approximation of SP mod U, or SP2n mod GLN is an approximation of what we want. Ignore that for now because I want to get to the fun geometry. Maps from P1 to the Lagrangian Grassmannian correspond to the following thing about bundles on P1. So they are by definition, if you unwind the functorial definition, you take the trivial bundle V, which is a rank 2n bundle, but has this beautiful alternating pairing on it. It's going to I want a rank n quotient bundle and a rank n sub bundle in the short exact sequence, and I want this will be a self-dual exact sequence on P1. This data is the same as a map from P1 to the Lagrangian Grassmannian. And so the recipe allegedly is that if I'm supposed to, given a map here, I should get a map here. So if I map spec of the complex number, spec of a field here, I should get a map from a spec of a field here, meaning that essentially what I need to figure out is if I give you any sequence like this over P1, you have to give me a vector space with a symmetric pairing. This has to give you, and furthermore, this is supposed to be an isomorphism in this homotopy category. So this should be somehow reversible. So I will tell you how to get from here to a vector space. That's easy, but with the symmetric pairing. Where does it come from? Well, you take this short exact sequence,
you twist it by -1 to get this. Oh, and my vector space is going to be similar to my previous blot periodicity thing. I want to just take global sections of E twisted by -1. E is globally generated. So this vector bundle has no H1 if you want. Okay, that's my A. Hold that in your head for a second. So start with this short exact sequence, twist it by -1, and take the long exact sequence. In the long exact sequence, well, you have H naught of this goes to H naught of this. H naught of this is 0, because that's a trivial bundle twisted by -1. Goes to H naught of this, goes to H1 of this, goes to H1 of this, which is 0 for the same reason. In other words, you have H naught of this goes to H1 of that. In other words, A goes, that's my definition of A. And by Serre duality, this is A dual. So I produced, just by, introduction to algebraic geometry, a map from A to A dual. And now the hard, head-hurting thing is that this gives a pairing, but it's actually a symmetric pairing. So my question is, why is it a symmetric pairing? And it's a head-hurting thing to figure out why it's a symmetric pairing. And then the bigger magic is that this construction is somehow reversible. Given A and essentially some affine information, you get enough information to magically reproduce these. And so once again, I'm saying this somewhat briefly, but there's a moduli space of maps of the Grassmannian. There's the moduli space of really BO of n, BO of something. And then if you have two spaces, they're mostly the same. They're affine bundles that are mostly the same. And then there's they converge, and these affine bundles change, and that's the underlying statement. That once again is telling you why this is true, and it implies that part of blot periodicity. So I have about 4 minutes left. So before concluding, I want to ask you questions. I've tried your patience enough, so I think I'll try your patience a little bit more. So the very last step of blot periodicity requires the last thing for the last step of all those steps was another analogous thing where there's one part that is unclear, and it feels like something that someone should recognize. So I just want to ask the question and take a couple minutes of your time. So once again, I want to take a free vector, a rank 2n vector space over. I'm looking for inspiration. So, and I'm sure if you do sort of complex numbers, it's good enough to work over an arbitrary base. Maybe 2 will have to be invertible. But okay, so let's say take a rank 2n vector, take a dimension 2n vector space with a non-degenerate alternating form. We've already talked about the Lagrangian Grassmannian. That came up we're just talking about Lagrangian Grassmannian. So the Lagrangian Grassmannian is going to be one of my 2 moduli spaces. The other moduli space are going to be vector bundles over P1 with a symplectic structure that looks like B. So it's a symplectic bundle. It's a vector bundle with an alternating form. And so there's going to be a similar sort of thing, and there's one missing part of this. So my question is this: if someone in the room later, after chatting, can tell me some affine bundle over the Lagrangian Grassmannian, that when you take a natural affine bundle, you get most symplectic vector bundles over P1. This I even know what it's supposed to be. I just don't see why it's an affine bundle. So someone in the right part of geometric representation theory should be able to just say, oh yes, this is a perfect example of something. And there's all the empirical, for those who are familiar with things, there's empirical evidence lying all around that such a thing should exist. And I'm sure that the resulting thing will be a quiver representation of some sort. So I'm hoping that one of you will have an idea like that and tell me what will go on. And that will be the last missing piece in this eightfold periodicity that will let us write that final few paragraphs. So my time is almost up. So I just like to summarize what I've tried to tell you, which is, so I'm trying to make the case. So homotopy theory and algebraic geometry, it's a very well studied topic, and why say anything basic about it? I want to point out that there are extremely fancy tools, such as motivic homotopy theory, which are tuned to solve very particular sorts of problems, and they're extremely powerful tools to know. However, there are certain very blunt elementary tools that will be useful almost never, but when they are useful, they will tell you very powerful things. So what I've tried to introduce is this setting that is simple enough that I really gave you all the definitions in the first 15 minutes of the entire talk. where everything I said is eminently checkable. And to say it again, you start with the notion of what are K-connected morphisms. They're just three axioms for what it means for morphisms to be K-connected. And then you have some things that are spaces, Cauchy sequence of spaces that got more and more connected. Again, these are invarieties. I will say invarieties, every invarieety I know that anyone I know cares about seems to get more and more highly connected in this way. But that's not a theorem, that's an empirical statement. So it seems to be the right category in which to work. The second are Cauchy sequence of stacks, where things converge, but you need some incurred spaces to have these visualizations. And finally, you invert all infinitely connected morphisms, and then you can start to talk about new kinds of spaces like PGL and these other spaces I discussed, which let you suddenly be able to make algebrogeometric sense of the kinds of arguments that topologists get to make every day of the week about stabilizations at the level of homotopy. But it's not just homotopy, all the things you want, the child groups, growth varieties, Frobenius, point counting, you name it, continue to live in this cheaply made categories. And as examples of it, I gave you 3 or 4 different examples, one of which was how to explain Bott periodicity and how it's really about vector bundles on P1, the topology of vector bundles on a curve, and then maps to the Lagrange-Grassmannian, and so forth. I'd like to see more if these naive tools can be applied in other cases, other things I'm hoping might work, but some are just vague dreams. But if you have any ideas, I would also like to hear them. So thank you very much for your time and attention.
So question is, when we invert these infinite connected morphisms, do you get some phantom maps, or do you have some relatively simple presentation for every one?
So in practice, you definitely have phantom maps, like the map from as an example of phantom maps you want. It's like the fact that BGM, which informally you think of as P infinity, you had before inverting P infinity map to it, and there just was no map in another direction. And another phantom map, which I think you really do want, is if you have a non-quasi-compact space, let me say, well, stat, but of course, but I'll say space to be less scary, like the space of vector bundles on a curve. It's not quasi-compact, but it's a countable union of quasi-compact things. And really the way you take this thing and put it in this category is you write it as this increasing union. And so if you were to instead allow yourself to put this non-quasi-compact thing in the bottom, you can't, like you're allowing, all the things the phantom ones I want to invert are ones I actually really would want to invert. But in practice, of course, there are, every interesting one has, the phantom inverses are ones I understand and believe. But you can't stop the fact that a morphism in this category, well, it might have a zigzag. That's going to be crazy and unbelievable. That's true. That's true. So yeah, so I want to say it's not as terrifying as the violence. Often inverting isomorphisms does great violence, and in theory this does. But I feel like I somehow feel like this is still geometry.
Hi. Yeah, thank you for the talk. So I wonder, is the affine line intractable in your category?
Yes, it's isomorphic to a point.
Okay, great.
And it's designed to be great, and of course.
Okay, so I guess the follow-up question to that is, to what extent do you think this, like without being too provocative, to what extent do you think this replaces this whole monotypic homotopy?
Sure, I mean, that is very provocative. I will say, but I will say very, very safely, it absolutely does not. But it does. I mean, I don't think it's at all provocative, which is like my attitude toward machinery is always there for a very good reason. And motivic and the axioms of motivic homotopy theory are exactly tuned to some problems, and they're tuned to a certain set of problems. And by building this, it was useful for a wide other set of problems. And so I do think that there's some hope for some more elementary things that people are just too used to reaching for machinery, because the machinery exists. Maybe they shouldn't reach for the machinery. And it should tell, so my hope is that there may be some simple things where it might be reasonable to just say, oh, look, really secretly, there's something more simple going on. But I think it's absolutely no limits. Oh, Kirsten's gonna say it.
Sorry, I guess,
I don't know.
no, we're here, I think.
Okay, so I guess.
So when you're talking about twofold block theory, you have this kind of magical quiver. I was wondering if you could say anything about where this like quiver comes from. I feel like I'm not the right person to say it because it's like a very obvious, like in retrospect, I see that quiver everywhere. So maybe I should really, there are a couple of things I should, well, I mentioned Hannah Larson and Jim Bryan at the start, and I should have had their names in flashing lights clearly, but with the quiver, it's Jim Bryan, and also the very clean description, like like the block periodicity that was with Hannah Larson, but the quiver, the clean quiver description, and then the meaning of the outline bundles from Jim Bryan. And so it's an extremely standard quiver that probably has a name. We call it the Strongman quiver because it comes from Strongman's exact sequence. But now whenever you have vector bundles on P1, you immediately go to that quiver. But Nakajima, it's like a very special case. It's like a trivial special case of a whole family of quivers. Nakajima does, or the ADHN quiver is like they're all. You can see all sorts of things in that world. And I don't mean better from this. I just mean that. But this is part of that. The quiver description of things on A2 and on one and P1 is just A1. So these are extremely standard quivers. But to me, it was surprising. I think it is a surprising thing. I think the Stroma exact sequence, the Stroma quiver, was rediscovered in history at least 3 times. And so I don't think it's something that you would. It's like it's not something. Yeah, it's quite unexpected. So I have no really good. My answer is I have no really good answer to where that came from. But one should always look for that.
I'm wondering if this version of bot periodicity specializes in anything interesting over fields other than RNC.
So, I don't. I see nothing. I think it's like really neat that it's something over everything, but over all spec C. But I don't see what it's like. I don't think how you would take it to the bank and make some money. I think it's you go to street corner and press people with how beautiful the universe is. So it would be nice, but I don't know. And I would not be surprised if someone, but if it were useful in that way, in some version of look at this point view of the world and do something with it, it's going to be something which has been seen in some other way, I'm sure as well. So I don't see. I really don't believe it's going to tell you something brand new about the world. Over here, 6-3.
One thing you could say about that is.
Oh yes, Ben goes.
It specializes to like help the block periodicity that exists for algebraic.
Ah,
It looks a little bit different because it has the motif, like the tape twist. So you don't get like a actual periodicity the way you might expect, but
because of the twist.
But that makes sense over FP. So,
Okay.
So like you do prove that statement, for example, which is at least something.
That's a good answer. So Ben will get better answers.
Thank you for the talk. I had a question about the functor. I'm here next to you.
Okay, great. Oh, Remy, okay.
I had a question about the functor to motivic spaces are actually relative to the homotopy theory of the homotopy category of the different spaces. But your category is constructed as a localization, right? Where you invert these. What if you invert them in the infinity categorical sense? Would that give you an actual function for the infinity category of motivic spaces?
I answer is yes. I'll refer. I know the answer is yes, but I'll refer the answer to Ben.
There's a functor from the.
Yeah, can you pass the mic to Ben? Is that he'll answer rather than he gives it out.
I don't want to say too much about it. There's a functor from like the two, it gets naturally two categorical of the way you go with it. There's a functor from that to infinite spaces. And so and it sends the things that he wants to say are equal to equivalences to equivalences. So then by a standard nonsense, it factors through the main infinity categorical organization.
Right, so one of the things that we like
specific spaces, so they were just cheap tokens, so things like seriously covers become co-limits in that setting. Just as there's varieties, do you still get things that cover the co-limits?
I need to say what the covers are, so I should be really careful, but these the covers, I can think of them. Some things I would want to be covers, they are, but the question is, are there other covers that I don't want to be covered with that? I think my answer could be yes for his risky cover, this is for adult coverage and smooth cover. But, yes, I'll say that, I'm not sure that's somewhat tautological, I'm not saying you can't see.
A really cool thing you can do in terms of homotopic theory is make a lot of full homology theories. So you've got a lot of flexibility to take quotients, and to build, homotopic theories in them. And, one of the things this is showing is that all those homotopic theories, that all those generalized homology theories, it has a version for stacks. So, I mean, you mentioned the chow, that there's chow bit and there's there's all sorts of motivic homology, and so that means that there's you know, there every homology theory is constructed in A1 homotopic theory is now getting version. That you can't just a priori have those homology theories inside this world, because this world is not something that is tautologically made to create homology theories. Well,
That is cool, yeah. That's a comment, that's a new comment to attempt.
All right, well, let's thank everyone one more time.